The ultimate objective of autonomous navigation is straightforward in theory. Calculate a path from point A to point B that a physical robot can actually drive. For decades, the industry standard for mapping that initial route has been a graph search algorithm known as A*. A* operates by dividing a mapped environment into a uniform grid. It then floods that area, evaluating the cost of moving from the start point to adjacent cells, isolating the optimal route cell by microscopic cell. This diagram shows the spatial result of that search. Because the algorithm is constrained to the grid's 8 directions of movement, the path it leaves behind forces a jagged, stepped pattern even when crossing wide-open spaces. This creates an immediate problem: geometric bloat. A standard A* output generates hundreds of redundant collinear waypoints stacked along simple straightaways. The first optimization objective is to strip the collinear bloat from the initial path, while guaranteeing the new route maintains strict clearance from all obstacles. This image shows the raw A* output, heavily saturated with redundant waypoints at every grid intersection. To reduce this density, the framework applies a line-of-sight pruning strategy. It stretches a straight line segment from the start node as far down the sequence as possible. The mathematical engine verifying these shortcuts is Bressenham's line algorithm. Bressenham's algorithm acts as a virtual raycast. If the ray hits an occupied cell, like this red dashed line, the shortcut is rejected. Conversely, the solid green line proves the straight segment passes safely through free space. The system enforces a strict decision rule. It places a permanent waypoint only at the very last verified safe cell, right before the line of sight is broken by an obstacle. From that newly established waypoint, the algorithm casts a new ray, repeating the straight line projection continuously until it reaches the final goal. Looking at panel B of the comparison, we see the output of this process. The dense web of nodes has been reduced to only 6 essential waypoints. In practice, this greedy line-of-sight strategy strips away 82 to 91% of the total waypoint count. The algorithm has successfully translated a bloated, high-density grid sequence into a hyper-compact, mathematically verified geometric path. Resolving the spatial bloat solves the mechanical problem, but it leaves the computational bottleneck intact for repeated tasks. Robots often operate in highly structured environments, continuously moving back and forth between fixed docking stations, assembly lines, and charging ports. Forcing the onboard processor to run a full A* pixel search from scratch for every repetitive trip creates a massive drain on processing power and battery life. The solution is dynamic path memory, a system architecture that caches optimal routes and retrieves them on demand. However, a system cannot cache every possible pixel-to-pixel coordinate combination. The memory requirements would be astronomical. The map's geometry must be simplified first. To accomplish this, the system uses convex cell decomposition. This visualization tracks the map's simplification process, beginning with the raw layup top left and moving to the decomposed regions top right. The algorithm uses a horizontal sweep line method to scan the grid. It partitions all accessible areas into brightly colored, non-overlapping convex regions. Convex shapes possess a unique and highly useful geometric property. Any 2 points located inside the same convex region are mathematically guaranteed to share a clear line of sight. Because the interior is safe, the computer just calculates borders, skipping the space inside. By carving the map into convex blocks, the framework transforms a heavy pixel-level calculation into a highly efficient, lightweight topological puzzle. With the regions defined, the system builds an adjacency graph, caching the precise optimal path segments between neighboring blocks. Looking at the center left panel, Step 1 identifies the start and goal regions. Step 2 uses Dijkstra's algorithm to sequence the region centers. Finally, Step 3 retrieves and stitches the cached path segments together, avoiding any grid cell scanning. This side-by-side analysis highlights the resulting efficiency. On the left, a standard replan expands 199 distinct nodes to find the goal. On the right, the memory retrieval system expands 0 new grid nodes, assembling the route entirely from its cached segments. This amortized O(1) retrieval drops the processing time significantly, delivering a 9.3x computational speedup for repeated navigation tasks. The robot pulls perfect, obstacle-free routes from its memory database instantly. The raw navigation data has now passed through 2 distinct optimization filters. This animation contrasts the starting baseline against the optimized result. A slow, dense 100-point line is replaced by an instant, clean 6-point path. Line-of-sight pruning acts as the spatial filter, solving the geometric bloat. Convex cell decomposition acts as the temporal filter, eliminating the computational drag. However, one mechanical flaw remains. The optimized cath is sparse, but its waypoints still form sharp, rigid angles. Physical machines are governed by mass and inertia. A wheeled robot cannot execute instantaneous heading changes without stopping its forward momentum entirely. This is where those sparse waypoints serve their final purpose. They act as perfect mathematical control points. Using these exact coordinates, engineers can weave continuous, dynamically feasible B-spline curves over the geometric route, translating pure grid mathematics into smooth, real-world robotic motion.